Hi guys. Today we'll be discussing a paper called Neural Ordinary Differential Equations and the core ideas that it presented and the research that has followed after that paper in the past 1 or 2 years. What the authors actually even like had in mind was to name the paper as training infinitesimally layered neural networks by backpropagating through black box ODE solvers. And to me, and almost like to most of the research community, this would make most sense. Like if we read this title, it actually would tell the gist of the paper, but they eventually went with neural ODEs because it was a catchy title. But yeah, the kind of issue that comes along with it is that it doesn't explain much about what the paper actually tries to convey. Um, yeah, so what I'll be going over is first just like an overview of neural nets and resnets, then what differential equations are and like how they are usually solved, like numerical methods for that, and then how neural ODEs have actually tried to bridge these two fields together and their applications that follow. So the original paper actually compared this with Resnets because that was one of the most straightforward thing to do. Is that we know how if we just see different layers in a neural net as discrete layers, saying after each layer we can call that each layer is performing some kind of nonlinear function. We can write the hidden states in this format. And then what we do usually in residual nets is we have some kind of skip connections where in addition to whatever output we got after passing in the previous outputs of the previous hidden layer, in addition to that we also pass in the outputs of the previous hidden layer. So in a sense, if we just uh, take like this h1 to the left hand side, you will see h2 minus h1 is kind of the residual. So instead of learning a whole new mapping with new layers, we'll like this function approximation for each layer will only be learning the residual mapping, and that improves many things, including something like vanishing gradient issue and few more. But what is of interest is how can this be related to how differential equations are written. So that was just a brief overview of how various information processing at each stage of a neural net is discrete because the number of layers itself is discrete. Now, if we were to like think of this in some kind of like expand our imagination and think of it as, let's not we don't want this forward pass to be over a discrete number of layers, but rather extended to some kind of continuous forward pass or like over continuous time and backward pass over continuous time. I'll get to that in a second, but before that I'll go over what how a general differential equation looks like. um, so usually, let's say if our variable of interest is x and it varies with time, so yeah, so we'll write dx by dt as some differential, which is a function which is dependent of the our variable independent variable x, and it also takes in input time, and it could be optionally parameterized by theta, usually is, which is a set of parameters, right? So what does it mean like when we solve a differential equation? It basically means that we have to integrate this differential over time. We start, so it's usually done either as a initial value problem or a boundary value problem. We'll just stick to initial value problem for now. But yeah, so it just means that at time t equal to t naught, some starting time, we know the, like, we take an initial value of our variable x, and yeah, from that, using just like the differential, like we put that value in x of at t naught in x of t, and eventually we put it in f, and we get the first like the derivative at that point. And then using a fixed time step, let's say some time step h, we calculate the next the value of x at next time step, and we do it till, let's say, some steps n plus 1. And yeah, so that is seen in this equation. It's pretty straightforward, and this is like the simplest method, called the Euler method. There are a bunch of much better fixed step methods such as RK45, which are very extensively used, and even a few adaptive solvers where the this time step is not fixed as something h. It actually adapts it, like it adapts itself to the curvature of the function, such that if it is curved near some points, then it should sample like more points near that part, so for more numerical accuracy. So this is basically what numerical integration looks like. um, yeah, and this is kind of interest to us, because there is no concept of time as such in like normal neural nets, right? Artificial neural nets. So when we actually so whenever we are going to use this in the concept of neural ODEs, just as a head start, we would we can think of it as time, or we can also think of it as some other variable depending on the application. And just like keep this in mind while we go over it, just as a heads up. um, Another thing to note is something as the fundamental theorem of ODEs, which is also of interest to us with a third application, especially with use to generative models, which is that the x of t is always going to be a flow, and what a flow means has various implications in like fluid dynamics and so on, and like mathematics. But in the simplest, like intuitive terms, it means that, let's say we have we take the time from 0 to 1, and we start with different initial values of x of t, and then we solve the differential equation and we plot the trajectories. The trajectories will not intersect, and that is a property of being a flow. And this is kind of interest while using it in generative models, because it helps us create um, special kind of one-to-one mappings, where the input and output dimensions are of same type and same dimensions and so on. Um, yeah, so when we try to bridge differential equations and neural nets, we can now compare with our understanding of the ResNet block, and what I'll refer to over here is as an ODE net instead of neural ODE. So we can now just try to compare equation by equation, and it will be more straightforward to see that now what we are going to try to do is that each discrete layer, which was passed through a residual block in a neural net, will try to not keep it discrete but make it continuous, and now treat it as it's passing, or it's being solved over time. And now that is kind of, eventually we have to compute things, so it will eventually be solved using some kind of numerical integration like Euler. So it will be discretized, but it will be solved using an ODE solver and not using just a forward pass through something like a fixed number of layers. And this can be more adaptive depending on the solver use. So that's why we can think of it as replacing something like a 6-layer residual net. They actually show in the paper that it can be replaced by one ODE solver of some like a large enough time step. Sorry, large enough time points. Yeah. So that's like the power of ODEs. So yeah, we can actually now directly see that the g of x kind of one-to-one corresponds to the differential in our ODEs, and now we are now characterizing our output of the past layer as something as the variables or a vector of variables of interest to us in that ODE problem, and which will be solved to the final time step to get our final time step, which is Tn, and that's what it means to do forward pass. So in a ResNet, the forward pass was pretty straightforward. Like any other neural net, you pass through all the layers. Over here, what it means is that when you do a forward pass through an ODE, you are like basically solving the ODE, and yeah, you solve it to the final till the final time step, in a sense. And so once we get to the final time step, now you want to backpropagate and learn the ODE in a sense. You want to learn the differential. So since we think of neural nets as universal function approximators, this f of x comma t is going to be like we can frame it in a bunch of ways. What the neural ODE paper actually suggests is like why not use a neural net, right? So and so now that actually reframes our question is how do we compute the loss with respect to the with respect to theta, which is now the parameter of that ODE, and which are actually the weights of that network. And so finding the gradients of the loss with respect to these parameters of the ODE is the problem which they actually try to solve. So if you were to, let's say, if you were to do it in residual networks, we actually need to know the activations after each layer, right? In order to find dl by sorry dou l by dou theta. So if you were to do similarly in with a differential equation, we would need to save all the activations over all the time steps from t naught to tn, such as like I need to save x at t naught, t1, and so on. So that's one way to do it, and it should be like possible. And yeah, it is the most straightforward way to do it. But what it does is that it takes up a lot of memory. So can we do better? Is the question that they ask. And yeah, there's a way to do it, and it's done using an adjoint method. Uh, and yeah, so what it does, it takes advantage of an adjoint relation, which was uh, yeah, which was brought to light by Pontryagin. I'm not sure if I've pronounced it correctly, but yeah, it's an old method. And what it says is that the relation it says is that the adjoint is dou L by dou X, which is the differential of partial differentiation of loss with respect to the variable of interest at each time step. That's the adjoint, and that also follows another differential equation, which is yeah, which is represented by this equation. So this is followed for all differential equations, and this is kind of an important step because this will now help us avoid saving x at each time step, but rather uh, what we can do is we can utilize this adjoint relation to directly calculate dou L by dou theta. So if we wanted to do that, I'm going to be like skipping through a bit of finer details in the math, but yeah. So let's have a look at this. Let's take this equation for granted that dou L by dou theta is going to follow this reverse integral from t. Okay, now there's a bit of change in the notation. The final time step, I'm going to be considering it as T1 instead of Tn. But yeah, that's the only change in notation right now. So from the final time step to the initial time step, we do the reverse integration of yeah this function over time, and that should give us dou L by dou theta. And in order to find that, we need to find each we should be able to find each part in this equation. So what they do is they use since this adjoint also follows an ODE, they just use three ODE solves. So basically, just as you can in a way solve an ODE forwards to do forward pass. You can also start from the final time step and solve the ODE with that as the initial value and solve it backwards to get x of t naught. This wouldn't have been necessary actually if we just saved the values throughout. But yeah, that's what we don't want to do. And now similarly, we can also do the same for finding the adjoint at the initial time step. And once we have that, we now have x naught, sorry, x and adjoint both at initial and final time steps, and those will be used in actually reverse integration for this. And over here, we assume the initial value is 0 of this uh, this function that we have inside. So that's an assumption. And eventually you'd think this is too much of work because like there are three ODE solves in place, but yeah, this all can be vectorized into just one ODE solve, and yeah, none of these are dependent on each other. So directly, like that one needs to happen over the other, and so on. So yeah, this actually ends up being just one ODE solve. Um, yeah, that was a bit too much of math, but this is basically a method to speed up the backward pass. So this helps us backward pass through the ODE itself. Um, any questions up until this point, and or else I can move on to the applications. Or else I'll take the questions in the end. I'll first go over the applications. Okay. So what the paper actually shows is that they show that this can be applied to a supervised learning setting, in a sense, just by like replacing the residual block of let's say 6 layers by just one ODE net, and it performs equally good, and that's all. They also show certain improvements in constant time performance in and like memory allocations and so on, but that was a bit far fetched is what they eventually say. Like in the end, I've attached uh, another video by David Dovenard. So he actually Duvenard, he actually talks over a year later about how most of the things in the or like few things of the neural ODE paper were hyped up, and few of them actually are not the right directions of research. So, what the right directions of research are actually using them in continuous normalizing flows, and most importantly in generative latent models. So, I'll quickly go over what it means to having like some kind of kind of continuous normalizing flows. Um, it basically use this property of ODEs that yeah, just solving an ODE over time is going to be a flow. So we'll find, yeah, neural ODEs are able to find a one-to-one mapping, which is a flow from any, let's say, target distribution to a noise distribution, and yeah, vice versa. And this actually is quite of interest because now this, because of neural ODE, it's going to be continuous in nature. Um, and yeah, so this has been again extended using FFJORD and a few more papers, but I haven't got into depths of those. The most useful like yeah application according to me is for time series prediction, and that's because what they do is let's say you have a time series of let's say up to m data points, and yeah, so you observe first n points and the remaining are unobserved, which you want to predict, and or like extrapolate and so on. So what the method that they propose and is kind of very useful, especially when later on when it was extended for irregularly sampled time series, which I'll get to, and it's very, in a sense, directly applicable to various kinds of medical and healthcare data. Um, so what they propose is that an encoder decoder architecture. You have a simple RNN encoder which takes in all the observed time steps one after the other and encodes it into a latent space which tells about um, the the mean and the standard distribution, standard variation, standard deviation. Sorry, for the initial value which we are going to use to solve or like yeah the rollout of the ODE. And what we will do is now we will use the neural ODE to actually yeah actually just create a rollout from sampling from that distribution, and then we can have the rollout for as many time steps as much we want. So we can also extend it beyond the observed time steps into the extrapolation region, and that will actually help us in a sense predict over time, which has some kind of underlying dynamics encoded in this ODE. Yeah, and that is represented by that network, which is the differential. So that's the basic idea of a latent ODE. What they eventually improve upon after a year is actually whenever, let's say, these observed time points were irregularly spaced, then yeah, we can use an RNN or some kind of recurrent unit whenever possible to progressively pass it into and encode the given information. But whenever we find a white space, or let's say few times time points which are getting skipped, then what it actually happens, oh, yeah, so what we can eventually do is whatever the ODE that is being learned, yeah, during the prediction, like we already have that ODE, so we can just use ODE solve to uh, solve up until the next time step, which up until where we have an observed value, and that helps us like, and that's the benefit of having and learned dynamics and using it throughout, and that can, in my opinion, we can do a similar stuff with also with just any simple differential equation which is not an ODE solve. We can still do that, but I haven't yet come across a paper which does that, but there should be one. So but this helps us tackle various healthcare problems or yeah, time series problems which use datasets like Mimic 3 or so on, where various different input signals are sampled at the same frequency of various different input signals is different, such as like heart rate might not be sampled equally possible as like some other signal. And yeah, and like the loss calculation is basically just two things. One is just yeah, some kind of MSE or yeah, just regression between the predicted output and the observed output, plus comparing the distribution using KL divergence. So there have been improvements to that, but yeah, I'll skip those for now. Lastly, like glimpse of like the latest research. Yeah, FFJORD is just a better continuous normalizing flow. I haven't read this paper in much detail, so I can't comment on this. But the rest three are of like more interest to me, so I've read them in more detail, which is augmented neural ODEs. What they show over here is that since this is yeah, this is characterized by a flow, there should be a few functions which it cannot essentially map. So that is a theoretical question. And they actually do show that, yes, there are a few non-flows which like neural ODs cannot model. And in order to model them, what it does is that it just adds another dimension to the state. So by here, state we mean is the variable of interest. So your x was the state and so on. So what they do is they just adding an extra dimension actually does help learn these non-flows much more efficiently. Um, Now over here, if we see that the in all these cases the yeah the neural net which was the differential was fixed in a sense. Yeah, it did not change over time. Uh, by time, I mean the time that is being used for the rollout in the forward pass. So these weights are learned, and those are learned for over like the whole backward pass in a sense. And these weights will be common for at each time step. Now, if you want to learn even complex mappings, which actually also learn or change over time, and then in that case, what they do is uh, NODEV2, what they propose is like two coupled differential equations where one is the differential of interest, which also varies over time, and then another function, parent function, actually encodes this weight network, which varies over time. So, in a sense, one just encodes the weights which varies over time, and the other encodes these weights. So, that is of interest only if we want the functions parameters to change over time. And yeah, they have discussed the representation possibilities of this paper in much more detail. Um, the most interesting paper from a neuroscience point of view or a dynamical systems point of view is that the ODE solver that we are using throughout OER, like the ODE that is being solved, we are using, let's say, a neural net as a differential OER, right? So because we are using them as, yeah, because they are universal function approximators and so on. But fundamentally speaking, like from a science point of view, that restricts our explainability and interpretability to quite an extent, where most of the phenomena in physics and neuroscience and so on are actually are actually framed in well-established equations, which are way more interpretable than just a neural net which is fitted to some data points, right? So let's say we have a bunch of these differential equation based models which were actually they were proposed for 40 odd years, and we want to use them and test their representation capabilities when used with a neural net in somewhat ways of dimensionality reduction only, like restricting the work that the neural net does to just dimensionality reduction, and like the main encoding is going to be done by the ODE. So what we can do is, instead of keeping the differential as a neural net, we'll keep the underlying state as some differential equation we all know and we all have studied over years. Let's say something like a Kuramoto oscillator model for neuroscience. Okay, so then let's say we are doing the same thing as what we did with latent ODE. Instead of just encoding the initial value, the LSTM, yeah, they change a few things, like they change RNN to N by LSTM and so on. And what they do is that now this will encode the mean and standard deviation of the initial conditions. Along with that, what it will also learn is the parameters of this ODE equation. So this theta, and now it's not a neural net, it's some it's some parameters we already know. So and this equation can be set of equations can be anything which is interpretable. So this over here encoder is doing some kind of dimensionality reduction. Let's say you're dealing with calcium imaging data or some kind of EEG data. These simple equations cannot model the finer things we see in real data, but the overall qualitative patterns can still be modeled using and understood well using these equations. So that heavy work of mapping this kind of dimensional reduction is done by the encoder, and again, while solving, the rollouts will be of the ODE that we all can interpret, and again generating more information to make sure it looks as if it's from some kind of real data such as EEG. That work is given to just a simple neural net as a decoder. Yeah, it need not even be recurrent actually. So just that works. And with this, the GokuNets has actually shown like few impressive results, such as um, the pendulum problem from, let's say, the OpenAI gym. If you just save a bunch of frames of the simulation of the pendulum with varying lengths of the pendulum, uh, it can actually regenerate the next frame in the video of the pendulum by just when all of it is actually encoded, not like the most of the information is encoded not with the like some kind of neural net, but just a basic differential equation that we know from high school physics. And like the length of the pendulum is a parameter that's learned, and g is a constant, and so on. So this, I feel, is a right direction for research, and currently I'm implementing this in Julia. Um, yeah, anyone who is interested in neural ODE, I have kind of skipped a few things which eventually these authors show or go over that, yeah, maybe that was a bit more hyped and could have been an outright lie or yeah, bullshit as what they call. But yeah, kudos to David, because he's like being completely vulnerable in this talk, which is awesome. Um and What I haven't yet gone through is a bunch of more papers which are also quite of interest to me, but I haven't yet gone through them. Again, these are a bit more biological and neuroscience related because if we and these are all from Ramin Hassani, who is now I think moving to MIT. So yeah, what they do over here is different kinds of worms have been well understood and much like better understood than human brains. So a C elegans is one such creature which is whose brain is like completely mapped, like each part of it and so on, and various equations have been derived from that, and they somehow bridge the gap between this and the current neural ODE framework. In a sense, if you see, like the original paper starts with something like comparing it with the Resnet and so on, but we can also, since I said continuous time, this can be thought of as a continuous time recurrent nets. So that's another lingo that's being used. Mm, so this is a very in-depth paper which I still have to read and has quite some fascinating results in a sense. What they do is that they have applied these units in computer vision, and when in a sense what they show is like whenever we are learning like road segmentation from while self-driving cars and so on, like applications in those kind of areas, they compare the attention between what a current state of the art computer vision system does and what using more biologically grounded networks do. So what the current system actually does is that it, it focuses attention on just the just the sidelines of the road, even as close as possible to human, like yeah, as close as possible to the car. But in real life, what we actually do end up seeing while driving is just like we focus on the end of the road, right? Yeah, near the horizon and not closer up to the car itself. And yeah, what they show is that the biologically inspired networks actually end up making more yeah, more human-like decisions and so on. Eventually, if anybody is more interested, best work to refer is yeah, Ramin's own PhD thesis, and it's huge and it's awesome. It goes in quite some depth, and do check it out if you are interested in this line of work. That's all, and open for questions. Yeah, I'll give a WhatsApp link. Yeah.